In April 2019, humanity saw something it had never seen before, a black hole, not a simulation, not an illustration, but a real image captured across the entire planet. At the center of a distant galaxy, an object so dense, so extreme, that not even light can escape it. What we saw was not the black hole itself. Black holes do not emit light, they do not reflect light, they remove it completely. And yet, these objects exist at the center of galaxies, including our own. At the heart of the Milky Way lies Sagittarius, a star, a supermassive black hole with a mass more than 4 million times that of our Sun. Black holes are not just objects, they bend time, they warp space, they challenge the very laws of physics, and the deeper we look, the more they remain a mystery. Now, what is really a black hole? A black hole is not a hole, it is not empty space, it is a region where gravity becomes so strong that escape is impossible. This idea comes from a theory developed over a century ago called general relativity. In this theory, gravity is not a force, it is the curvature of space-time itself. Mass bends space-time, and space-time tells objects how to move. The more mass you have, the more space-time curves. If enough mass is compressed into a small enough region, that curvature becomes extreme, so extreme that all paths lead inward. This is a black hole. At the boundary of the black hole lies something called the event horizon. It is often described as the point of no return. But it is not a surface. You cannot touch it. You cannot see it directly. It is a boundary defined by the structure of space-time. Beyond this boundary, no signal can escape, no light can return. And once crossed, there is no turning back. Near a black hole, light behaves differently. It bends, it curves, it wraps around the object. This is known as gravitational lensing. Light from behind the black hole can be bent around it, creating distorted images. This is why black holes appear surrounded by glowing rings. What we are seeing is not the black hole itself, it is light fighting against gravity. One of the most fascinating effects is what happens to time. Near a black hole, time slows down. This is not an illusion, it is a real measurable effect. Clocks closer to a black hole run slower than those farther away. To a distant observer, an object falling toward a black hole appears to slow down. Its movements stretch, its signals weaken, its light becomes redder and dimmer until it fades completely. It never seems to cross the boundary, but this is only one perspective. From the perspective of the object falling, everything feels normal. There is no visible line, no sudden barrier. It continues inward and crosses the event horizon without noticing a dramatic change. This is one of the most important ideas in physics. Reality depends on how it is observed. Two observers can experience the same event in completely different ways, and both can be correct. As the object moves closer, it begins to experience tidal forces. Gravity is stronger on the side closer to the black hole and weaker on the far side. This difference stretches the object. Over time, the stretching becomes extreme. Matter is pulled apart, layer by layer, atom by atom. In smaller black holes, this happens quickly. In larger ones, it happens more gradually. But in all cases, the outcome is the same. Once inside the event horizon, the rules change. The direction toward the center becomes unavoidable. It is no longer a choice. It is as inevitable as time moving forward. There is no path outward, no escape route. All possible directions lead deeper. This is not because something is pulling you back. It is because space-time itself gives you no alternative. As we approach the center, our understanding begins to break down. Physics predicts a singularity, a point where density becomes infinite and space-time curvature becomes infinite. But in science, infinities are warning signs. They tell us that our theories are incomplete. At these extremes, we need something more, a theory that combines gravity and quantum mechanics. We do not yet have that theory, and so, beyond this point, certainty ends. For a long time, black holes were thought to be eternal, objects that only absorb and never give back. But this changed with a new idea that black holes can emit radiation. This is known as Hawking radiation. At the edge of a black hole, quantum effects come into play. Pairs of particles briefly appear and disappear. But near the event horizon, one particle can escape while the other falls in. To an outside observer, this looks like radiation, and over time, this causes the black hole to lose mass. Very slowly, it begins to shrink. This leads to a deeper question. If a black hole can disappear, what happens to the information inside it? In physics, information cannot simply vanish, but if black holes evaporate, where does it go? This is known as the information paradox, and it remains one of the greatest unsolved problems in modern physics. We know that black holes exist. We have observed their effects. We have measured their influence. We understand how they form. We understand how they behave from the outside. But beyond the event horizon, we cannot see, we cannot measure, we can only predict, and those predictions have limits. Black holes are not just objects, they are boundaries, boundaries between what we know and what we do not. They bring together the largest forces and the smallest scales. They expose the gaps in our understanding, and they push us toward new discoveries. When we look at a black hole, we are not just looking at darkness, we are looking at a limit of observation, a limit of knowledge, a limit of understanding. And beyond that limit lies something we have yet to fully grasp. Perhaps one day we will understand what happens inside. Perhaps we will discover a deeper theory that explains everything. But for now, black holes remain both understood and mysterious. They remind us that the universe is vast, that our knowledge is still growing, and that beyond every answer, there are still questions waiting. And yet, even with everything we understand, black holes continue to challenge us in ways that go beyond observation. Because at their core, they force us to confront a deeper question: how complete are our current theories? For decades, physics has been built on two powerful foundations. On one side, we have general relativity, which describes gravity and the large-scale structure of the universe. On the other, we have quantum mechanics, which governs the behavior of matter at the smallest scales. Both theories have been tested extensively. Both work with extraordinary accuracy. But inside a black hole, these two frameworks are forced together, and when that happens, something breaks. The equations no longer agree. The predictions no longer align. This is not a small problem. It suggests that our understanding of reality itself is incomplete. At the center of a black hole, physics predicts a singularity, a region where density becomes infinite and space-time curvature becomes infinite. But in science, infinity is not an answer. It is a signal that something is missing, that our current models have reached their limit. And beyond that limit, we need a deeper theory, a theory that can unify gravity and quantum mechanics into a single framework. This is one of the greatest goals in modern physics, and black holes sit at the center of that pursuit. They are not just extreme objects, they are laboratories where our theories are pushed to their absolute limits. They reveal what works, and more importantly, what does not. And in doing so, they guide us toward new understanding. But even as we search for answers, black holes continue to raise new questions. If nothing can escape, what happens to the information carried by the matter that falls in? Is it destroyed? Is it preserved in some unknown form? Or is our understanding of information itself incomplete? These are not philosophical questions. They are deeply scientific, and they sit at the intersection of everything we know about the universe. Because if information can truly disappear, then one of the fundamental principles of physics would be violated. And if it cannot, then black holes must behave in ways we do not yet understand. This tension between what must be true and what appears to happen is what drives modern research. It is what keeps black holes at the forefront of scientific discovery. And it is what ensures that they remain not just objects of study, but gateways to deeper knowledge. Because in the end, black holes do more than challenge physics. They challenge our assumptions about space, about time, about reality itself. And as we continue to explore them, we are not just learning about black holes, we are learning about the limits of human understanding. For most of human history, the universe appeared stable, predictable, almost permanent. Stars were fixed points of light, galaxies, distant and unchanging. But black holes tell a different story. They reveal a universe that is dynamic, violent, and constantly evolving. Stars are born, they live, and eventually, they die. And in some cases, their death leads one to something far more extreme than anything we see in everyday reality. A black hole is not just an end. It is a transformation, a transition from one state of matter into something we do not yet fully understand. At the centers of galaxies, these objects play a crucial role. They influence the motion of stars, they regulate the flow of gas, and they shape the structure of entire systems. Without them, galaxies would not behave the way they do. And yet, despite their importance, they remain invisible to direct observation. We do not see the black hole itself, we see its effects. We see stars moving at incredible speeds around something that cannot be seen. We detect energy released from matter as it spirals inward. We observe distortions in light that reveal the presence of extreme gravity. And through these observations, we build a picture, a model, based on evidence and grounded in physics. But even the best models have limits. There comes a point where observation ends and theory begins, and black holes sit exactly at that boundary. They allow us to test how far our understanding can go. They show us what we can explain and where explanation breaks down. This is what makes them so important, not just as objects, but as tools for discovery. Because every time we encounter a limit, we are given a choice to accept it or to push beyond it. Science has always chosen to push, to question, to explore, to go further, and black holes represent one of the greatest frontiers in that journey. They are not just distant phenomena, they are part of a larger story about how the universe works, a story that is still being written. With every new observation, every new theory, every new question, we move closer to understanding. But we are not there yet, and perhaps that is what makes this so compelling, that even now, with all our knowledge, there are still mysteries waiting to be solved. And yet, even as we expand our knowledge, black holes continue to hold their silence. They do not reveal what lies within. They do not allow us to observe their deepest structure. Instead, they force us to think differently, to question not just what we know, but how we know it. Because in most areas of science, we rely on observation. We measure, we test, we confirm. But black holes introduce a fundamental limit, a region where observation ends and inference begins. And that changes everything. It means that part of reality is permanently hidden from direct access, not because of technology, not because of distance, but because of the laws of the universe itself. This idea is profound. It tells us that there are boundaries to what can be seen, boundaries to what can be measured, and possibly boundaries to what can be fully understood. But science does not stop at boundaries. It studies them. It uses them as starting points. Because every limit reveals something deeper. Black holes are not just obstacles, clues about the nature of gravity, clues about the structure of space-time, clues about how the universe is fundamentally built, and perhaps most importantly, they are clues about what we are missing. Because if our theories cannot fully describe what happens inside a black hole, then those theories are not complete. And that is not a weakness. It is an opportunity, an invitation to go further, to develop new ideas, new frameworks, new ways of thinking. Throughout history, this is how progress has been mad. Not by avoiding mystery, but by confronting it. Not by settling for answers, but by asking better questions. Black holes represent one of those moments, a point where knowledge meets uncertainty, where certainty can gives way to exploration, and where the next breakthroughs are waiting. Perhaps one day we will understand what lies beyond the event horizon. Perhaps we will discover a theory that unifies everything, a theory that explains gravity, quantum mechanics, and the true nature of space-time. But until that day, black holes remain what they have always been. Objects that we can describe, but not fully explain. Phenomena that we can observe, but not directly access. And reminders that the universe is far more complex than it first appears. When we look into a black hole, we are not just looking at darkness. We are looking at a boundary between the known and the unknown, between understanding and mystery. And beyond that boundary lies something we are still trying to reach. So the next time you look up at the night sky and see the stars scattered across the darkness, remember this. Somewhere out there, in that vast expanse, are objects that do not shine, objects that do not reflect, objects that do not reveal themselves directly, And yet, they shape galaxies, they bend time, they influence the universe on the largest scales, silent, invisible, and powerful beyond imagination. Black holes are not just part of the universe, they are part of the story of how we understand it, and that story is still being written.